if this is how the Friday class, if I let you to go on Zoom, is going to be, you're not gonna have Zoom part. So I'm making this Friday to be on Zoom to help those of you that don't have access to computer to be in the class. Well, if you're here, you're here. If you're not here, means that you're taking advantage of this, and I'm gonna make all the classes in person. And your learning will suffer because you don't actually have access, right? So the whole idea is to help you, not to give an excuse not to attend the class. I mean, if you're here and listening, you already are part of the, so I guess it doesn't matter, they're not gonna watch this. So we will tell them on Monday, remind me. All right. I am going to start. Brett will check the chat. So if you're here, raise your hand for question, because it's difficult between Discord and chat and then
exit.
So just use the chat if you're in Zoom classroom. If you're here, just raise your hand. I'm still showing my face. I don't know, whatever. We discussed that, it's okay, you can see me. I do something about this guy, so I can actually remove that, right? There. Huh. How about that? Could be smart. So how do you do full screen? And then full screen. This can stay up here. Oops. Okay. Stay there. All right, so today I will talk about the two things. One is the remaining of frequency domain. We didn't finish it, so it will not finish today, but I will create two sections. One, maybe about 20 minutes to 15 minutes, talk about the frequency domain, and then I'll go to MATLAB. So for the first part, with the first part, you can solve your class participation for this weekend, all right? The second part is just ongoing design example. If you didn't finish, we will pick up next week, all right? So when we are dealing with frequency response from the body plot, if you remember, I mentioned that, I mentioned that we need to know where to look at, right? From the time domain frequency, from the time step response is very clear for you. Now, from the body plot, we have two cases that we want to look at. So first case is, so assume this feedback loop that I have there. So you have a system, you have some controller. So I put PID and there's a feedback loop, right? So if you think about an open loop response, which you don't have the feedback coming into you. So the system does not see the feedback. If you send a sine wave, all right, if this sine wave has 0-degree phase shift from the output, you send an input, you get an output. Now, if you wanted to look back at it and see the difference, since the phases are the same, or they are 0-degree phase difference between input and output, the error you get is the actual error of the system, right? Now, if this phase, there was a phase shift of 180 degrees between your input and output, it would mean that when this block is seeing the error in the second case, and we have -80-degree phase shift, is going to add the error, right? Because the error will be twice as the actual size. So it will give us a fake error. Then the system controller tries to compensate for that, and the system goes unbounded and unstable. So it wouldn't be the magnitude of the system, it would be the phase shift. So we don't want the controller plus the system have phase shift of negative 80 degree, 180 degree. So that's the bad thing. That will drive our system to instability. So our system on its own might not be unstable. When we design a controller, we might create that phase shift from the output with the input that the controller sees an excess error that doesn't actually exist. So when we are looking at body plot, we are going to look at that negative 180 degree phase shift at 0 dB. All right, so we're going to go to more details, but this is one of the points that we want to look at. So if you are at 0 dB and 0 phase shift, we are going to be marginally stable. So you're in a stable area. But if we go beyond that, if our phase shift is negative 180, is that the worst case scenario. Now, between 0 to negative 180, we want to see how much room we have to wiggle. All right. I think someone asked, it was Adrian, like what is phase, like phase margin and gain margin when you're looking at a body plot to solve the class participation, right? So those are the margin that you can design your controller, and as long as you're between those margin, you're good. And the boundary is set at negative 180 degree. So we are going to discuss that today. So this is basically the idea behind why we are looking at those 2 points. So physically, the two sine wave signal from input and output will create a fake field of an error for us. Now, looking at a body plot, if you see a huge peak, like here on the left side, so if you see this huge peak, excess peak in the closed loop system, that should tell you that your system is probably close to be to that unstable value. So now what is huge? How do we measure, right? We are engineers. Huge is not a good way of explaining things. So a rule of thumb is if our gain is more than 6 dB, we are entering that huge. All right. So here the gain is 20 dB, which is greater than 6 dB. So this means that this system is sick. It needs to be fixed, needs to be controlled. Now, this is a symptom that you observe, oh, there's not something wrong with this system. This is not the problem. The problem comes from, if you look at the phase plot, which is, so if you look at the plot on the right, my right, your right also. So if we look at the open loop system, this red line is the open loop amplitude out, which is our gain. Why am I losing this guy? This is the gain, and this is the phase, right? So the gain is here, dB, this is the phase. All right, now let's look at those 0 dB. So this is 0 dB, right? So if we look at the phase, the gray, we will see that the phase at 0 dB is somewhere here. So it's going to be 174.5 degree. This is very close to that negative 180, right? And we said negative 180 is bad. So this is the problem. So the problem is that our phase margin or amount that we are far from negative 180 is so small. Then we see the symptom is that high gain. Now, again, Dr. Z, what is so small? You're an engineer, you don't have just use adjectives. So as a rule of thumb, as control engineers, we like to be above 30 degree for phase margin, the amount that there's a difference. So if it is 30 degree, we are good. So when you're designing a controller, when you look at the response in body plot, measure that. And if it is 30 and above, you're good, right? So, now, if we also look at our gain here, negative 35 dB. So, also small gain margin, but sometimes 35 is good enough. So we will check both of them and see which one is too small and which one is dangerous. So why is 35 good enough? Well, we want it to be far from 0, right? So 35 is farther from 0. We have to look at other system specification. So this is from like visually, if you see a big peak, you know that, okay, something must be wrong. Then you go and check the phase margin, right? Now, we are going to define both of them, how to find them. And then from there, you just look at the body plot, go find these two values and look at them and see what is their value. And you can tell about the stability of the system, if it is stable or not. For more information, then you need to look at other things, all right? But this will be good enough to give you a hint that, hey, I need to fix the system. Now, how many of you know what phase and gain margins are? Raise your hand, please. Okay, good. So I can explain everything from the beginning. So to find gain margin, how many of you know what gain and phase of a system are in the body plot? Raise your hand. Okay, let's step back before I go to gain and phase margin, because gain margin is different from gain and phase margin is different from phase. They're related. All right, so what is the gain of a system from a body plot? Do you remember how do we plot body plots? We discussed that on Wednesday. Zoom, students, put in the chat, what do you think? Where do we find gain? What is gain? What is phase? How do you find them? How they are related to body plot? From the audience, raise your hand. If you're in my 3090 class, don't raise your hand because you already know. What is gain and what is phase in a body plot? You can also cheat from the Zoom. Connor, what is gain? What is phase in a body plot? What is a body plot?
It displays the gain and phase.
Yes.
And particularly the gain in the unit decimal.
Okay, so good. So you know what they are. Now, you know the relationship between body plot. On body plot, you know what they are. Now, how do we find the gain? That's the question, right? So body plotted all of those. Thank you, OSU, for funding him. So we don't have to do by hand, right? Someone did it for us. You could actually plot body plot by hand. This is part of this class. I'm not teaching it because we can use MATLAB. So you're skipping over hand stuff, sketching by hand. Now, how do we relate the system to its body plot? What output of what? Input of what? Let me help you. Julia, transfer function of a system, right? Now, transfer function is in S domain. We are here in frequency domain. What happened? Adrian, what happened? You did this, so you know. Huh? You don't take a Fourier. Why would you do that? Why you make your life so hard?
I forgot which one it was.
It's not the Fourier for sure. James, you remember? It is so S is Laplace, right? This is frequency. So you need to go to frequency domain. There is a very quick way of doing it. J omega, right? And omega is what? Excuse me, put your feet back inside. Yeah. So what's that frequency? Frequencies, all the frequencies, right? So you put 0 and put it in transfer function. So the omega here is the variable in your system. So you're in omega domain instead of being in time domain or S domain. So you put omega 0, you find the value of the transfer function, it will be a number. You put it right there. So if I knew what the system transfer function was, and I put omega equal to 0, well, let's say I'm gonna continue that. This would have been the number. So let's say this is omega 0.1. This is radian per second, right? If I put that, this is the value of my gain, whatever that is. I don't know. Gain maybe is -2 dB. Now, Transfer function is volt per volt. It's not dB. How did I get dB from? Well, we have a very beautiful equation. 20 log of volt per volt is dB. You get that? Why do we do that? Because logarithmic scale is a lot better and easier to see, crunch the numbers so they can fit better. And we can see the changes over that. And that's how the body plot, the gain part of it is plotted. So when we say gain, you're talking about gain of the transfer function. It comes from there. So you basically plotted the response of your system in all possible frequencies, right? What would be the gain of the system? Now, how about phase plot? It must be the same thing, right? But what is the phase? You remember this, the lag time between input and output? So we are looking at each frequency, what would be the lag time between our output and our input? And since we are in LTI, our omega remains the same, our frequency, so we just have different times. Omega t is the phase, that's the angle, right? Then we put the phase over there. So both of these are characteristic of our system, is the response of the system to different frequencies. Okay, it is really important that you are able to explain this. All right, using body plot, interpreting it without knowing why did you plot this? It's like, okay, I'm gonna pass this course and I'm gonna forget about it because I don't care. Because next time you see a new system, you don't know what to do. How do we get to this part? Make sense? All right, now let's go back to gain margin and phase margin. Okay, so to find the gain margin, I mean, erase all of this. First, we are going to, okay, don't let anybody in anymore if they were not in the class. It's 20 minutes late. Okay. All right. From now, please don't get out and we're not going to let you in. So from the phase plot, this is really important. To find gain margin, we are going to look at the other plot. Phase plot is the one in the bottom because it says phase in degrees. Gain is margin and magnitude in dB. All right. So from the phase plot, find the intersection of body plot with, guess what number is the number of interest in our phase plot? Negative 180, because we want to avoid it, right? Negative 180 degree. So it means that the blue line is my body plot, right? This is the phase margin. So I'm gonna draw a line, this yellow line from negative 180. I draw that, and then whenever this intersects, I'm going up because this is phase. You can go down also, but it doesn't give you any. So you read it here. You keep going up until it crosses now your gain, your magnitude plot, right? So this frequency that you find here or here, this is your omega PC, crossover frequency. So this is called crossover frequency for omega PC. So phase crossover frequency, because we found it from phase. Thank you. Yeah, I forgot. I mean, probably wrote too fast. All right. So we found our omega PC. So we have a frequency that the phase is going to be negative 180 added, right? Now, if we continue and intersect with the gain 3, find the gain. I'm going to call it G0 at omega PC. So this is omega PC, this is G0. Now, gain margin for GM, that's not the car manufacturer, is 0 minus G0. Why 0? Not the maximum. You remember at 0 dB, we didn't want to be at negative 180. Here. At 0 dB, we didn't want to be at negative 180. So now we found the 180. We also want to find the 0 where it is. And we want to know how much we have until we get to that. So this becomes the GM. So this is 0 minus negative G is the amount, right, you have until you get to 0. So this is the margin you have. Because if you're at 0 and negative 180, the system is unstable, right? If you're at 0 and 0, the system is critically stable. So you're gonna just cross over to the unstable part. So 0 dB is important, all right? It's not your maximum gain. Now, I'm gonna write stuff for phase margin in pink. So you can see the difference. So for phase margin, we are gonna start from the gain plot, okay? 1 from gain plot. Does this look like 1? Find frequency that gain is what? 0. So this is omega GC, all right? Then let's find that. So from the phase plot, we are gonna see where, so this is the 0 line, and then we're gonna go here, so assume this is right on there. Just want it to be there. So that's 0, so this is that omega, so let's say this is omega GC, which is also the same thing here, omega GC. We call that omega GC, and then find P0 at crossover for gain crossover frequency. So here, this is P0. So your gain phase margin, or PM, is going to be P0 negative 180 degree, because you're finding the distance between here, right? This is your phase margin. Rule of thumb was we like the phase margin to be greater than 30. So minimum of 30 degree phase margin. So rule of thumb, PM greater than 30 degree. You can say equal also. Fine. All right. Now from gain and phase margin, from the values you find, how do we say the system is stable or not stable? Do I have room there? No, I'm going to write up here. So if your GM is greater than 0 dB, not including 0, greater than that, this is a stable system. If your PM is greater than 0 dB, it's a positive value, so it means that there is some value between you have some margin, stable. If you have PM0 and GM0, this is critically, or no, marginally stable. Now, if you have a marginally stable system from oh, degree, start with D. Yes, thank you. So if you have PM and GM0 from the body plot, you're looking at the body plot and you realize, oh, you measure both of them are 0. What does it tell you about the poles of the system? There is at least one or pair of poles that are on the imaginary axis, right? So they're all related. It tells you, if you look at the response of a system, is going to be oscillation and is not gonna die down, right? So there is a relation between all 3 of them. So if you know about one of these domains, you have information about the other 2. So I want you to always think and be able to connect them. Because right now, you know all 3 of them, all 3 domains. How do we look at the response of them and what each of them mean? Yes.
The closer to zero the neighborhood growth, you also talk about how more
Yeah, how stable they are, yes. So we are gonna talk that on Monday because I need more time to discuss those. Yes, it's the same. You can even find the poles from the body plot, the values of pole, because pole S is J omega. If you have the omega, you know where the pole is, right? So you could even say if it is a conjugated pair of conjugate or just one, if it has a pole at the origin or not. You can give all those information, interpret from body plot, all right? At least the hope is. So you'll be able to do that, go between all three domains. All right, any questions on this from Zoom classroom or from the classroom? Jill. Jeffrey, what's your question? No question? Okay. No, nothing from Zoom because I have I didn't read these things. Yeah. Cool. All right, I'm gonna stay on this. So we are going to solve or review a design problem. All right, the problem is simple. I'm using it to give you some ideas about body plot, then we go to our actual design problem. So this was the first part of the class that we finished talking about body plot. Can I move from this slide, Joe? All right, so we have a system. We want to find out the K range, the values. So when we say K range, here K is a compensator, right? So your system G of S is 1 over S times S plus 4 to the power of 2, right? You're designing a K controller and we want that the system, what do we want? Oh, okay. So we want to know the stability or instability of the system. We want to know what is it at K equal to 1, and then for what case we can make the system stable. So this is just to show you this. We will continue more on this on Monday. All right. So one thing, first of all, what type is this system? Type 0, 1, 2. What's the system type? Everyone in Zoom, please type. And you can show by your finger. Raise your finger. Amber, what system type? Why? Okay, you can. Why? Yes. Okay. Set. Okay, so that's not the reason. You're kind of correct. So the power of this is what tells you what's the type of system. S to the power of 1, which means you have 1 over S, one integrator in the system. So I know what you're trying to say. You need to be able, so if you tell someone, this is type 1 because it's K over S. How do they know it's because of the K or over S or what 1 over S means, right? So there is one integrator in the system, or the power of S is 1, which relates to one integrator in the system. That's how we define system type. That's why we use a PI control to make the system type 1 if it is not, or add 1 to the type of the system, right? So make sure you connect what you learn and repeat it, because it helps you to get intuition when you're designing your controller. All right, so this is system type 1. Now, I'm gonna show you a magic trick, all right, that I will tell you without looking at the response of the system that this system is unstable. And I'm gonna show you. How do we know, like, how do we go about telling the instability or stability of the system? We look at the denominator, right? So here, the denominator is S times S squared plus 8S plus 16. And if I open that, S is S cubed, 8S squared plus 16S. All right. So I talked to some of you about this, but I thought it would be good if I talk to everyone. So if you have a polynomial here, like the denominator, if you are missing any power of the S, so here we are missing S to the power of 0, right? That's the power of S that's missing from this polynomial. This system is going to be unstable. For some case, for some compensators, this system is going to be unstable. It means that if you draw the root locus, where are some of the branches going to be? On the right side. So I predicted this. I haven't thought, but I used this example before, but it doesn't matter. You give me a system, I'll tell you. If you have all the coefficients, it doesn't mean the system is stable or not. You can't draw any conclusion, but if one of the coefficients were missing, one of the powers of S, definitely unstable for some value of case, meaning that there's some part of it that goes on the right-hand side, right? Make sense? I mean, do you understand? Okay, so now I know for some value of k, this is going to be unstable. I'm going to draw root locus. Ta-da, I was right. This is the unstable region. So it doesn't mean that the system is totally unstable. No, it will have some part that is stable. But when you're designing K, like a KP controller or a gain, you need to know where not to put it, right? For those that will make the system to be on the right-hand side. So this is just good intuition and understanding before you even start the design, because you need to be careful not to pick any K. So when you're trying to give KP some values, you know, for designing PID controller, you need to know, oh, there are some that I cannot put, because if I do, look at the response, it's going to be unstable. All right. Now, this is the root locus. You know, you create the system from here. If you're coding, you create the system from your favorite method, then R log of the system will give you this. Now, if you do the body of the system, all right, and the step of the system, you're gonna get these two. Look at the step response, unstable for k equal to 1. So I put k equal to 1, right, and see the system is unstable. Now, from the body plot, if I wouldn't look at this, if I didn't plot the step, could I say from the body plot? So is this unstable? What is this? Huh? It's not stable. It's also not, it's marginally stable, right? Because it's bounded. So it's not going outbound. So if we look at the body plot, what are the phase and gain margin? What do you expect it to be? Both 0. If we look, they're both 0. When you do body plot, we have a command that we can plot GMPM, but you see it's calculated, they're both 0. So from all 3 of this, and look, why? That's the cause, right? So you saw the symptom. The cause is if there is poles on the imaginary axis. And you should be able to observe this from any of the plots. So for k equal to 1, this is unstable. For all this region, this is going to be unstable. I'm going to give k a different number, but we will discuss on Monday how to find the k that the system is stable. But let's say k is 128. We will learn why this number is good. And step response, who is that? Okay, fine. I'm micromanaging here. All right. So step response, stable, reaches to 1, no steady state error. Now, if you look at the body plot, you have PM of 88 degree greater than 30, be good. And this one is positive. Both of them are positive, right? And is this a good system? We don't know. We don't have all the specification, right? Is it fast enough? Don't know. We don't know what was the specification. But we know, is it stable? There is no steady state error. Correct? So, good, depending on what you want. All right. So, now you can switch to MATLAB. I'm gonna also switch to MATLAB. You can use your lecture slides, but I already coded all of them, yes.
So, is it possible, like your mean margin and phase margin?
Yes, yes, you don't want them. If it is unstable, yes. So, from your lecture, slide 10 is telling you about damping ratio and natural frequency. I think I already went over that. But is this the same? Yes, this is the same system. So I'm going to plot that. I'm going to separate this line. So first plot root locus. If I have the grids on, you can see the natural frequency. And so this one is your omega, and these line, the radian lines, radius are your zeta, right? So you can find, if you have zeta and omega requirement, you can find those, and then you know which region the system is stable or not stable. Then there is another very, very useful tool. So it's called rlocfind. So I'm going to run the whole thing. When MATLAB runs this line, you can use the cursor like and then pick a place, a point in your S domain. Every point in S domain is a pole, right? So basically you can click on a pole, and it will tell you what would be the K that you need to design so the system will have a pole in that region, that point. Do I need to repeat that? It was a very long sentence. So when you run rlocfind, you can use this. Is a little bit slow, and every point on this plot is a pole, right? Could be a pole or zero, right? So it's trying to find the poles. So if I want my system to have a pole, let's say here, if I click in the command line, you will see that it tells me, oh, great. What are those poles that I chose? Because I clicked on imaginary, like I clicked inside, so those are going to be conjugate, right? I didn't pick a real axis. I picked somewhere that there was imaginary component and real. So it tells me what poles I clicked on, and then so what is the K value that gives me those poles? So you're placing a pole in a system if you choose K to be this value. Now, if you look, I can move this up here. If you look, there is the imaginary, and then there is a real, because it's thinking that, okay, if you just, maybe you just wanted to pick on a real axis, okay? But if I want the real axis, I would choose the real axis. So just trying to give me. So this, you can use it for if you're designing like controller based on pole placement, and you think if I had a pole here, the system would be stable, and then I don't move faster. Pick a region, really, like it's not random, but you don't know what the exact value is, right? You click, it will tell you. If you put K equal this number, you will have a pole here. Your system pole, all of them, because it knows the system. All the poles will change because of that, right? And it will tell you where the pole is going to be. So this is very useful to give you intuition inside when you're designing a controller, right? Now, what is pole in physical sense? You know, like, hey, I have a motor, DC motor, and I want to get this velocity out of it, and I want to design a control that places a pole. In physical sense, what is that pole? Right? Because pole doesn't have a physical meaning. What are you trying to do by adding that pole to your system? You should have been asking me this question 3 lectures ago, but I'm asking for you. Yes. Because S is J omega, right? So you're looking for that frequency. Good job. So it also means the other way around. If your system has poles at -1, -2, what does it mean? At those specific frequency, my system behaves specific ways, right? So S, pole, 0, they don't mean any physical sense. That's why they are the bridge between the two domains that we understand them, but they're so far apart, like to connect them to each other, or see them at the same time together, that someone introduced, how about S domain? Let's talk about them together, and then we can always convert them. All right. So you are thinking in terms of frequency. That's why body plots are so important, because you see the frequency response right away. All right. I think in your, I don't know, I'm gonna just assume again, in your 2020, did you plot body plots? So from there, you should be able to tell from the slope of your body plot how many poles your system has, right? You can tell that. There are also ways to find where those poles are. So body plot could be sufficient for you to find all the information. So what frequencies are interest? Okay, let's see what happens at those frequencies. All right, cool. Well, I'm excited. So this was just the practice. The code is, I think, I uploaded this code on Carmen, so you can literally copy paste. All right. So I think, I don't know. The next code, which is the design example, that is on Carmen, definitely. So this one was not really important. The other code, this one is on Carmen, is on, it says, I think like root locus design example or something. So copy that, so you don't have to code. Open the text box, copy all the code, paste in your, yeah, today's. This week, today. I mean, it would make sense, right? Wilson, why you are being a spectator and spectator? All right. So I want you to, once you have that, don't run the whole thing, run step by step. So run and advance. So clean everything and then create your system. And we want to look at the response of our system. Ooh, what is that? Query the system is unstable, or we need to fix something. What's wrong with the system? When you get something like this, what should you think about your system? Your system is unbounded, is going crazy. Okay, good. Now let's look at the root locus of the system. So I'm going to put it in here. All right. Axes are, so if I change the axes, all right, so you see that the system for some values would be unstable, right? So we expected to see some sort of instability in this. Now, we have two system requirements, zeta equal to 0.7 and omega n equal to 1.8. So you can use S-grid to show these zeta and omega values. This is the cool part. So do you see, I don't have grid on, but here actually shows, it's the same thing that you do when you use by hand, right? Omega n and the zeta value for your radius. Not do that value. Now, try to use rlog find, okay? So you have the command. Pick poles about negative 2.88 or negative 2.8, negative 3, and 1.2i. Somewhere. So why does it not turn on? I thought I did. Grid on. S grid on. I think. Yeah. Ooh. It just turned the grid on. Okay, let me do that again, the whole thing. Slightly slow. Are yours is slow too or not? Is this me? As it runs. Okay. I'm gonna take this out. Run from top. Or like fine. So it would have both my root locus, and then I can what happened here. Run that. Advance. It did not delete it. And run this section. Okay, we are back in business. Now run this section. All right, great. So we have our body plot and we have our zeta and omega. Now run this section. Now let's choose something. Say around here. So K equal to this value gives me this pole. So the idea is we can put those K value and poles in a vector. So then you can call that K and use it in your control. So that is the pole placement part. So if you know where you want to place your pole, you can place and look at the pole that are chosen. If it's good, you already put K you saved it, right, in a vector. So you call that, you use that K in your controller. Now let's say we are gonna give a value of K equal to 370. We are going to create a feedback system. This was already in your exam, right? So you get a feedback of multiplying K times your system. And then you can run this section, you can see the closed loop response of your system. Then from there, if you're doing pole placement, you see if you're meeting your system requirement. All right. So how do I see my system response? I go here, characteristic, let's say settling time, and whatever else I want to know. You have to go back to your system characteristic, which omega n and zeta came from, and see if they are met. So this is pole placement method to design a controller. What does pole placement mean? We're gonna end after this. So what does pole placement mean? Anyone from Zoom? Yeah. Yes. So do you remember if we plot the root locus, some part of root locus are unstable, so for some K, And we need to change the shape of our root locus. So we know so pole, it's like a magnet. Wherever you put it, the rest of the root locus will go toward that. All right, it will change the behavior of the system. Now, sometimes, if I put a pole here, I'm changing the behavior of my system because I have a certain frequency I'm interested in them, right? So pole placement is, what is pole? 1/s plus something, right? So you're adding a pole to your system, that's pole placement. Now, certain K values, when you have access to root locus, if you choose those Ks, it translates into adding a pole to your system because you have, well, you can see there, I'm gonna write it, hold on. Okay. So if you have a system K, G, right? We discussed this in root locus. So if you want to write the transfer function of the whole thing is 1 kg over 1 plus kg, the feedback loop. So you're changing because of this K, there will be a difference in the poles of their system. So a pole will be added to your system because of this K, right? So one way is to calculate and know what exactly the value of pole is. One way you don't know. You can use rlog find, the same method that I showed you, that piece of code. Say, I know it should be around here. You pick, and then you have a K value. You plot your step response and check if you're meeting the requirement. If not, if you're close, you know the pole has to be around there, right? Start changing your Ks, which result in a different pole until you meet the requirement. This is a controller design, right? So far, PID controller, lead lag, and pole placement. That results in a gain. So gain is your controller, just a gain, like a K, but the impact is that you are adding a pole to your system because of that equation. You're manipulating the denominator, right? Okay, so we're good here. I already showed you the system designer. Next Friday or maybe on Monday, I don't know yet, we will continue on the design example. You also don't need password for your class participation. All right.